Hello, welcome back dear students to the tutorial about the spectroscopy. We have been discussing about rotational spectroscopy. In the last video, we had discussed about the effect of isotopic substitution and I think the intensities of the spectral lines, and we have studied that. Firstly, we have studied that in the case of rotational spectroscopy, all the lines are equally spaced in the rigid rotor approximation, and the separation between the lines is equal to 2b. Okay, and intensity, from the studies of intensity, we have seen that the intensity increases with the increasing J value and reaches a maximum and then decreases. Intensity depends on two factors. First, the population, and that is the Boltzmann factor e raised to minus delta E by kt. And secondly, the degeneracy of the state, and degeneracy of rotational levels are 2j plus 1. Okay, and in isotopic substitution, if a heavier isotope is substituted, then the value of B decreases. Okay, this much we have discussed in the last video, and today in this video we are going to discuss about the non-rigid rotator. Okay, listen. So okay, actually the rigid rotor approximation, we get the constant 2b separation of the energy levels in the rigid rotor approximation. But actually the spectrum is not like that. If you look at this table, it is a rotational spectrum of hydrogen fluoride. So experimental values, and you can see here this is a B value, and you can look here the B value first is 20.56, 20.48, 20.43, 20.31 and 19.82, 19.16, 18.91. This is the J value increases. With increasing J value, we expect in the rigid rotor approximation B to be constant, but here we can see that B gradually decreases with increasing J value. Okay, this prove that the rigid rotor is only an approximation. Actually, the bond is not rigid. Actually, we know the bond is elastic, and there will be vibration. Okay, and here also we can see here the bond length calculation of bond length to be constant, but you can see here 9.0929, 0.0931, 0932, 0935, 0938, 0941, 0946, 0951, and that is gradually bond length increases. Okay, and this increasing bond length and decreasing B value is with the increasing J. That means higher the J value, that is higher the speed of rotation. With the increasing J value, speed of rotation increases, and increasing speed of rotation, the bond will vibrate, bond will stretch and compress. Bond is elastic. Therefore, the B value decreases and also the bond length also increases. Okay, we know that the rotational constant B is equal to h divided by 8 pi squared IC. Okay, when the bond is not rigid, then we know that this is equal to B is equal to h divided by 8 pi squared, I is equal to mu r square C, and that is B is inversely proportional to r square. So when bond vibrate, bond stretches and elongate with the increasing J value, the R increases, therefore B decreases. And that is the effect of non-rigid rotator. We want to study this more. And that is if we assume that if the vibration is simple harmonic, and that is only an approximation, then bond stretching and elongation are in the equal extent. Then the average bond length will be equal. But for example, if you consider a bond length of 0.1 nanometer, if it stretches to 0.1 nanometer and compresses to 0.09 nanometer, then the average is equal to R average is equal to 0.011 plus 0.09 divided by 2, and that's equal to 0.1. Actually bond length is same here. But here we know that in this case average bond length is equal. But if we consider 1 by r square, then 1 by r square average value of 1 by r square is equal to 1 by 0.09 square plus 1 by 0.011 square divided by 2, and that is equal to 103.05. Okay, and from this we can calculate R average. Yes, that is 1 by R square increases, therefore B will decrease. Okay, and next, okay, if we solve the Schrodinger wave equation for non-rigid rotator, the energy equation will be like this. That is Ej is equal to h square divided by 8 pi squared I into j plus 1 minus h raised to 4 divided by 32 pi raised to 4 I square r square k j square into j plus 1 the whole square joules. Okay, and we're here, and if we convert this into wave numbers, that is epsilon j, and that is equal to Ej divided by Hc, and we get this is equal to H divided by 8 pi squared Ic into j plus 1 minus H cube divided by 32 pi raised to 4 I square I square r square kc into j square into j plus 1 the whole square. Okay, and this we can try. This is equal to, we know in the first studied that this is equal to h divided by 8 pi squared I is equal to b. This is b into j plus 1 minus, and this term we can write it as d. So it is equal to d into j square into j plus 1 the whole square. J square. Okay, j square into j plus 1 the whole square. And this b is rotational constant we know, and this d is called centrifugal distortion constant. Centrifugal distortion constant. Okay, from this equation we can see that, and this that is this d is equal to h cube divided by 32 pi raised to 4 I square r square kc. Okay, I square r square kc, and here this d increases with the increase in k, where k is the force constant here, k is the force constant. So increasing the value of k, the value of d decreases. That means stronger will be the bond. K is the force constant. Force constant is higher for strong bond. When bond will be stronger, the value of d will be very small. So for stronger bond, the deviation from the equation, the former equation, will be less. Okay, and if vibration is anharmonic, in the previous case we consider this vibration is harmonic, simple harmonic. If we consider vibrations to be anharmonic oscillation, then the equation will be like this. That is Ej, epsilon j is equal to b into j plus 1 minus d into j square into j plus 1 the whole square plus h into j cube into j plus 1 the whole cube, k into j raised to 4 into j plus 1 the whole raised to 4, etc. But normally this h, k, etc. are very small, so they can be neglected. In all these textbooks we are omitting this anharmonic oscillation approximation. We are considering oscillations to be simple harmonic. So this much is needed. Okay, so we can connecting b and t, b with d. Okay, that is d, we got d is equal to h cube divided by 32 pi raised to 4 I square r square kc. That is d. Okay, this we can write h divided by 8 pi squared IC the whole cube, okay, into, sorry, okay, so to be 8 cube we have to multiply it with 16. Then only this become, we can try here at 8 cube, 16, and here only pi raised to 4, we want to pi square raised to 3, pi raised 6, therefore we have to multiply it with pi square. And I cube, we want I cube here because I cube is to be needed. We can only I square here. Okay, so we can try this is equal to 1 r square is already here. Already 1 r square is here. We know that I is equal to mu r square. So we have to multiply it with mu. Okay. Then c, only one c here. We need c cube. So multiply with c square. So we can write d is equal to, and this is b cube into 16b cube into pi square mu c square, and one k should be here. This, the k is here, divided by k. And this is this equation. That is d is equal to, that is we get d is equal to 16b cube pi square mu c square divided by k. Substitute the value of k. K is equal to, actually the value of k is equal to 4 pi square omega bar square into c square mu, or mu c square. That is the value of k. Substitute that value here, we get 16 b cube pi square mu c square divided by value of force constant k is equal to 4 pi square omega bar square mu c square, and this is cancelled, pi square cancelled, 16 by 4 is equal to 4. So we get 4 b cube divided by omega bar square. So this is the relation between d and b, that is d is equal to 4 b cube divided by omega bar square, where omega bar is the vibrational frequency in wave numbers, vibrational frequency. And that is in the order of, actually the normal vibrations are in the order of 10 raised to 3 centimeter inverse, and B we have studied that order of 10 centimeter inverse. Therefore value of D is approximately 10 raised to minus 3 centimeter inverse. Okay, so this is a very small value, and we know that our equation is, this is our equation, that is epsilon j energy of the rotator, non-rigid rotator, epsilon j is equal to b into j plus 1 minus d into j square into j plus 1 the whole square. The value of d is 10 raised to minus 3 centimeter inverse, is very small. So smaller the value of j, smaller the value of j, we can calculate this term. Or the value of b will be as same as the rigid rotor approximation. When the j value increases, higher value of j, that is j increases from 5, 6, 7, 8, at that time this term become prominent or significant. In that case the value of separation decreases. So normally in the lower j values, separation somewhat same as that of the rigid rotor approximation. With increasing value of j, the lines become more closer. Okay, this you can see in this diagram. That is, this is a non-rigid rotator. Okay, actually in the non-rigid rotor approximation, or in the non-rigid rotor case, the energy levels decreases. You can see here the energy levels are decreasing with increasing j value. Okay, and here also this is a spectrum. Actually in the non-rigid rotor approximation, we get a constant 2b separation. Okay, lines are obtained at 2b, 4b, 6b, 8b, 10b like that, and there is a constant 2b separation. But in the case of non-rigid rotor approximation, you can see here actually it is 2b, then almost constant, no problem. Here also almost constant, but after the J value from 8b onwards, you can see this separation decreases. Here also decreases, again decreases, decreases. With increasing J value, the separation between the lines, you can see, decreases. And that is a consequence of the vibration of the bone. That is a non-rigid. Actually, the molecules are non-rigid rotator. Okay. Then, yes, this is the selection rule is same as that of rigid rotor approximation. That is delta J plus or minus 1. So, if we calculate the frequency of the transition, that is from J plus 1 state to J, that is epsilon J plus 1 minus epsilon J, we get the frequency of absorption nu bar J, energy of absorption frequency nu bar J, and that is equal to B J plus 1 into J plus 2 minus J into J plus 1 minus D J plus 1 the whole square plus into J plus 2 the whole cube minus J square into J plus 1 the whole square. I think you are clear it. That is our equation was this. That is epsilon J is equal to B J into J plus 1 minus D into J square into J plus 1 the whole cube. Therefore, epsilon J plus 1 minus epsilon J is equal to B into, for J we have to substitute J plus 1. So, J plus 1 into J plus 1 plus 1, that is J plus 2. Okay. And minus epsilon J, that is B into, already B is taken outside, so J into J plus 1 minus D can be taken outside, J square into J plus 1 the whole cube, sorry, whole square. Okay, so for J, first we have to substitute J plus 1. So J plus 1 square, J plus 1 plus 1, that is J plus 2 square minus, and this is also outside, minus epsilon J, that is J square into J plus 1 the whole square. That is this equation. B J plus 1 into J plus 2 minus J into J plus 1, D J plus 1 square J plus 2 square minus J square into J plus 1 square. By solving this equation, we get this is equal to 2B into J plus 1 minus 4D into J plus 1 the whole cube. I think you have remember in the case of non-rigid rotor approximation, rigid rotor approximation, the epsilon J plus 1 minus epsilon J, that is nu bar J, is equal to 2B into J plus 1. Here also same equation, 2B into J plus 1, but an additional term minus 4D into J plus 1 the whole cube. That spectrum will be same as that of rigid rotor approximation, but the 2B separation, the separation between the lines decreases by a factor of 4D into J plus 1 the whole cube, and the displacement or the closing of the levels increases with the increasing, or it is proportional to J plus 1 the whole cube, or higher the J value, the separation between the lines increases. That we have seen in the spectrum already. Okay, then this is about non-rigid rotor non-rigid rotor. There is only one thing you have to remember, that is when the J value increases, the lines become more closer, because when with the increase in J value, the rotation speed increases, therefore bond length increases, B decreases. Okay, and the energy equation is Ej is equal to epsilon J is equal to B into J plus 1 minus D into J square into J plus 1 the whole square, where D is the centrifugal distortion constant. And the relation between B and D is equal to 4B cube divided by omega bar square, where omega bar is the vibrational frequency. Okay, which is the order of 10 raised to 3, and B is in the order of 10 raised to 10. So actually approximately D is in the order of 10 raised to minus 3. It is very small value. But in the case of our equation is d into j square into j plus 1 the whole square. So for smaller j value, that term can be neglected, but for higher j values, the value will be significant. Okay, you have to read the textbook very well. Okay, thank you.